So first, let me start with a brief introduction. So our research focus is we try to develop some efficient spatial-temporal clustering algorithm that can identify some dense regions in the point cloud stream. So here, this figure gives you an example of the location stream. So we have the longitude and latitude. We have the time. So it's very simple, just three-dimensional data. And so the algorithm we propose, we name it ST-COPOT. Let me start with the input and output of the algorithm. So the input, again, is very simple, just point cloud stream, and we have a region to where you collect the data. And the output is spatial-temporal clusters. And in our case, it's the graphs of the related spatial clusters here. So after I give you, later on I'll give you the experimental results, so you will have a clear idea what the output will look like. And since we try to cluster the streaming data, so what we do is, again, very simple. We try to divide all the data into temporal batches. So we have time windows. So then we try to identify the continuing relationship between the consecutive time windows. So next is the overview of my algorithm. It's a three-phase serial approach. The first phase, we just get a spatial function. So we get a density estimation of all the points inside each batch. Then we come to the next phase. What we do is we use all the points within one batch. We identify the dense regions. We identify the spatial clusters for multiple density thresholds. So basically, we have a hierarchical clustering result for each batch. Then at last, we come to the last step. We try to identify the continuing relationship. So we try to identify whether the spatial clusters still exist in the following batches. So now let me go through the three phases in detail. So first phase, we just use a kernel density estimation. So we have a two-dimensional density function for all the points inside each batch. That's what we do for the first phase. And in our implementation, we use the normal distribution as the kernel. So next is the phase two. So since we have limited time, I'm thinking I will skip all those details, but I will give you a figure. So this figure, I think it kind of explains the phase one and phase two very well. So on top is the density function you might get for all the points collected in each batch. And on the bottom, so for the phase two, what do? We try to we use the contouring algorithm and some post-processing, because sometimes you might get a hole. So instead of a hill, you might get a valley, right? So we use some contouring algorithm and some post-processing. Then we identify the hills for each batch. So, and again, this is on the bottom is an example result of what you may get for each batch. And so the thing is that we might get more than one hills, right? So this is what we define. We define a data structure called the contour polygon tree. So that's what our name comes from, ST-COPOT, contour polygon trees. So this is an example of what you may get for each batch. So we have two hills. So this region means what? It means that you have high density of the points, right? So, and here, I just give an example. Here I use 3 density thresholds. And if you go inside the region, the density goes higher. Yeah. And so now we come to the third phase. So after the second phase, you already get the dense regions. So how do we add the time to it? That's the question. So does the cluster still continues or it disappears, right? So what we do is we propose a set of distance functions. There are like 7 or 8 distance functions. So the distance function what does the this distance function do is it calculate the distance between the contour polygon trees you identified for consecutive batches. So the most basic distance function is the top. Let me use the. Oh, sorry. Oh, yeah. Oh, sorry. Okay. Yeah, the most basic this function is this one. So what it does is just calculate the overlap of two polygons, right? So this value, as you can see, is between 0 and 1. So 0 means what means that these two polygons overlap. So all the other distance functions, they are extended from this one. So they all have the range between 0 and 1. So if it's 1, it means what? There's no overlap at all, right? So it basically means the spatial clusters, it disappears in the next batch. But if it's 0, so it means it's the same, right? So we set some threshold, like a 0.3 or 0.4. If the overlap is really high, it means it continues. So it means it still exists in the next batch, in the next time window. So since we might have multiple contour polygon trees, that's why we need multiple distance functions. So we have distance functions for the contouring polygon. We have this function for the continuing contour polygon trees. We have continuing function for the full resolve contour polygon trees. And so next, let me give you some experimental result I have. And the data set I'm using is the New York City taxi trip data. And for this data, it has the trip information. For each trip, it has the starting, the pickup time, the drop-off time, and the pickup location, the drop-off location. It's not trajectory, just the pickup and the drop-off. And so here I use the 1 day data set to demonstrate my algorithm. And the 1 day, it has like 430,000 trips. And so this is some interesting result I found. Like early in the morning, there are 3 regions, as you see. One is southwest of the Times Square. The other one is near the 34th Street Penn Station. And there's one, I think there's one over here. This is the Grand Central Terminal. So we infer that for the New Yorkers, after they get off the train or bus, because of these 3 dense regions, they're all near the bus stations and train stations. So we infer that, so early in the morning after people get off train and buses, they choose to use the taxi cabs. And so this is the afternoon and the evening. We find from 2 to 8 a.m. we have dense regions at the West 34th Street, and then it disappears in the following batch. So you might ask, so what's the information? So you might ask what we can use the information for, right? So the thing is, if we know the demand of if we know the demand change of the taxi, it can help the taxi companies to allocate the taxis, right? So that's one application. And on the late night, as you can see, there are dense regions around the Times Square from 10 p.m. to 4 a.m. And so the other application is using this kind of information, you can help the taxi drivers to locate the customers also, right? So you know where there are a lot of people who need the taxis, right? Also, so this is just an example. I use 2 hours as one batch. So you can use this. So you can basically using this approach, you can identify the hourly pattern, the daily pattern, the weekly pattern, and the monthly pattern. And if the data set is really huge, if the data set is really large, the time complexity can reach as approximately linear time complexity. So that's our goal. We try to, like with what I said in the beginning, we try to develop some efficient algorithm for the streaming data. And next is some related work about this area. There are a lot of existing clustering algorithms, but the thing is that most of them, they cannot apply to the streaming data. And or even though there are a lot of density-based clustering algorithms, but none of them use the contour algorithm or contour analysis. So that's the kind of novelty of my work. And so next is the future work. So what I'm thinking is recently I'm thinking try to apply this algorithm to the event detection in the Twitter, because we have the geotag tweet. So maybe we can find some interesting patterns using my approach, and by combining some natural language processing techniques. Yeah. Also, because currently all the parameters are kind of choose the parameters by myself. So later on, I might need to investigate some automatic parameter selection algorithm. Yeah. And that's all my presentation. Thank you.
So thank you for that presentation. Any questions for our speaker? Oh, in front.
I'd have curiosity, approximately what is the runtime for the algorithm?
Oh, because the thing is that in the phase 2, we try to grid the map. So for example, if the grid is 300 times 300, that's 90,000, right? But if we have millions of points, so this grid size compared to the data size is nothing actually, right? It's kind of a constant. So even though the actual time complexity is the grid size multiply the data size, but if the data size is really large, we will ignore that constant factor. Yeah.
So then how long did it take you to run the simulation?
For this simulation, I think a few minutes, maybe. Yeah.
I wonder if the size of the grid will influence somehow the shape and the size of your polygons.
Sorry.
So smaller the grid size of the bean of the grid
Yeah.
versus much bigger bean size for the grid, that will influence the shape and the size of the polygons.
Yeah, that's true. So the result I show you is kind of like it's really small grid size. If you use large grid size, you can see the polygons actually, like 3 edges, 4 edges. But right now, because I use a really small grid size, so it's approximately like a circle, right? So the other thing what we are trying to work on recently is try to estimate how the parameters affect our result. Yeah, that's one thing we are working on. Yeah, thank you.
Other questions? Excellent. So let's thank our speaker one more time.